Hi, everybody. This is a quick screencast presentation about energy. Now, generally, energy is something that is more thoroughly studied in a physics course, but anytime that matter changes, there are energy changes that accompany changes in matter, sometimes very big energy changes, sometimes very small energy changes. But it's important for us to have some basic vocabulary to associate with those changes so that we can understand them. So we're going to work on that. We're also going to try to differentiate the difference between heat and temperature and learn about a few different temperature scales and learn how to interconvert among those. Okay. So first of all, you guys studied energy in ninth grade in the physics portion of the course, and I think you learned that that energy is the capacity to do work. Hopefully, you remember the unit for energy, which is a joule. We'll talk about joules. We'll also talk about calories in here and definitely practice some conversions between joules and calories and some other energy units. Some vocabulary that you need that I think you will remember, hopefully, from ninth grade is one of them is kinetic energy. Okay. And kinetic energy is the energy due to the motion of the particle. Now, one of the really important things about kinetic energy is that average kinetic energy is proportional to the temperature of the sample. So if we compare, for example, two different beakers of water that have, the same amount of water, let's say in both of them, and one of them's at a higher temperature, then we know that that beaker has a higher kinetic energy and the particles of water that are in that beaker are moving faster. If the second beaker, of course, has a lower temperature, then we know that there is a lower kinetic energy in that beaker, lower average kinetic energy, and that the particles are moving a little slower in that colder beaker. So this is going to be a really nice, important relationship for us to be able to, compare the temperatures and be able to compare the average kinetic energy of different samples. And then there's potential energy, which is stored energy. Mainly in chemistry, we'll talk this year about energy stored in bonds and energy due to the position of the particles. You would also maybe talk about batteries in AP Chem. And I know you learned a lot of different ways in general science that energy can be stored, like a ball sitting at the top of a hill has potential energy due to its position relative to the bottom of the hill. So, but we'll really stick to potential energy as it applies to chemistry and matter. So some other vocabulary that you definitely need to have is that of endo and exothermic processes. So an endothermic process, it's thermodynamic, meaning that it's, heat is thermodynamic, means that it's changing, where heat is flowing into a system from the surroundings. So I'd rather just have a pen here than a highlighter. So anyway, let's say, for example, that I've got like a beaker of, water, and I put that over, the flame of a Bunsen burner. Okay. It's attached to my ring stand. And heat is going to flow from the Bunsen burner, right, into the system. That makes this an endothermic change when I boil water because heat is flowing from the surroundings into the system, with the beaker of water being the system. If you have an exothermic process, that's one where heat flows from the system to the surroundings. So you might wonder, well, what's an example then? Well, the reverse process, let's say like you're in the bathroom and you've got a lot of steam, and that's just a little random line there. But if all those little dots are like little water molecules in the air, and then you have a mirror, okay, another lovely random line. I see I'm going to have a little trouble with that. Sometimes I do. Let's say you have a mirror or a window and it's cold outside, so the window's cool. Okay. If we look at the steam that's in the air as the system, okay, if heat flows from the molecules to the cooler mirror or the cooler window, then the little molecules of water, okay, they are going to go to a lower temperature, and they will end up condensing into liquid water on maybe the surface of the mirror or the window. And in this case, heat flowed from the system to the surroundings, with the mirror and the water being the surroundings. So these are opposite processes. When you boil or evaporate something, it's endothermic. And then when something is condensed, that is exothermic. So we'll learn about a lot of different processes that are endo and exothermic, but that's just good vocab to have. Overall, when energy does change during these processes, it cannot be created or destroyed. So the total energy is conserved. Like if you go back to here, all the heat that's given off by the system has to be absorbed by the surroundings and vice versa. Okay, so energy is conserved, just like you have learned in the past about the conservation of matter. So what's the difference between temperature and heat? Are they related? So temperature, as we saw in that other one, is average kinetic energy, okay? Whereas heat is the total kinetic energy of the particles in a sample. Let's say that I have 2 beakers of water at room temperature. Okay, this one has 100 milliliters of water in it. Another lovely random line, because that happens. So this one has 100 milliliters of water, and then I have a bigger beaker, and it's got 500 milliliters of water, okay? And if they are both at room temperature, that means that they have the same average kinetic energy of the particles. But this one over here has more total kinetic energy because there are 5 times more particles, okay? So it's like, let's say I have 10 students in period 1 and I have 20 students in period 2, and I give a test, okay? Both classes get a 90% average on the test. But if I counted up the total points earned, period 2 would have more total points just because there's more people, okay? Does that make sense? So temperature is average kinetic energy, where heat is the total kinetic energy. And so that's a really important distinction to know. Now, we have a couple different temperature scales to measure that average kinetic energy. The first two, the Fahrenheit and Celsius, they are both based on properties of water, okay, and named after a scientist. It was Gabriel Fahrenheit and Anders Celsius. And basically, if I could draw a little bit here, like if you say, okay, here's the boiling point of water, and down here is the melting point, or let's say the freezing point, because we'd have to have the water turning into get melting point and freezing point of the same temperature. Down here we have the freezing point. Basically, what they did was assign a number to these fixed points. Okay, and we have to add that it's at normal air pressure. We'll learn a little bit later on in this course that boiling point can really fluctuate a lot with air pressure. But on the Fahrenheit scale, okay, it is 32 degrees Fahrenheit and 212 degrees Fahrenheit. And then they just divide in between there into 180 even steps, and each one of those steps is called a degree. On the Celsius scale, it's 0 degrees Celsius and 100 degrees Celsius. And so in here, you would just divide it into even steps, and there's 100 steps on the Celsius scale. So you can see that like the steps on the Celsius scale, they need to be a good bit larger than the steps on the Fahrenheit scale. I mean, they cover the exact same change in kinetic energy, but there's only 100 steps, so each step has to be bigger. In fact, there are 9 steps on the Fahrenheit scale compared to every 5 steps on the Celsius scale. it's a 9-to-5 ratio. Basically, I just take 180 to 100 and, and reduced it. So that really ends up giving us equations for conversion. Basically, there's also a differential here. You see this of 32. So to go from Fahrenheit to Celsius, if you take the number in Fahrenheit, you got to subtract 32 because we got this 32 offset right here. Okay. But then we also have to account for the fact that the steps are, different sizes. So there's 5 steps on the Celsius scale. Boy, that's a little messy. There are 5 steps on the Celsius scale for every 9 on the Fahrenheit. So if you take whatever your Fahrenheit temperature is and you subtract 32 and then you multiply by 5/9, that'll give you the temperature in Celsius. Now you can rearrange this equation. You got to take the Celsius, you got to multiply both sides by 9/5 first and then add the 32, and that'll give you the Fahrenheit. So notice when you're using these, that's a really important point, is that up here, let me get a little highlighter. Up here, you have to do the subtraction and then multiply. Down here, you have to multiply and then add. Okay. But both of these are equations that you should write in your notebook, because you're going to need to be able to do conversions between them. So pause this and do this conversion right here, and come back and we'll see if you got it right. So to complete this conversion, we're starting with a number in Fahrenheit. So when you start with a number that's in Fahrenheit, you take that number, okay, and you subtract 32. Then you take your answer times 5, divide by 9, and that'll give you an answer in Celsius, okay? If you got, for this one, 37 degrees Celsius, then you got an appropriate answer. I know that sounds really weird when you're thinking about, normal body temperature would be 37, like, 39, I have such a fever. It would just sound very weird to us, but a lot of places, they do use temperatures on the Celsius scale as their regular everyday temperatures. We're one of the few countries that does not. So normal room temperature is considered 25 Celsius. You'll see a lot of different data in chemistry is quoted at 25 Celsius. And you think, what's so special about 25 Celsius? That's considered normal room temperature. So just kind of, again, pause that and practice converting that into the Fahrenheit. And then hopefully you pause that and you did complete the conversion. Okay. This time you want to take the Celsius temperature and you have to multiply it by 9/5. Then add the 32. And that will give you the Fahrenheit temperature. And for this one, you should have ended up with 77 degrees Fahrenheit, which is considered normal room temperature. I don't know about you, but I keep my rooms a little cooler than that. So in both the summer and in the winter. So questions there. So hopefully you can interconvert between them. There's also the Kelvin temperature scale. We will talk about at some point this year, I should say very soon, but in a couple of units, about the development of the Kelvin temperature scale. It came from work with gases. Now, the Kelvin temperature scale, also named for someone. Each degree on the Kelvin scale is exactly the same size as a degree on the Celsius scale. It's just that they shifted the 0 point to the spot where a gas would have absolutely no volume and absolutely no kinetic energy. So we'll look at this later when we do Charles' law, looking at the relationship between the volume and temperature of a gas. They could extrapolate back and say, all right, this is the point at which this line is going to cross the x-axis and be at 0 volume. And we have to call that 0 temperature, because you can't have less than 0 volume and you can't have less than no kinetic energy. So it is the lowest possible temperature. and it's actually equal to negative 273.15 degrees Celsius. So the steps are exactly the same size, so the conversion is easy. All you got to do is take the Celsius temperature and add 273.15, and you'll get the Kelvin temperature. When they write a Kelvin symbol, they don't do like a little degrees Kelvin for some reason. They just do, a K. So that's something that you want to make a note of. But it's very easy to convert. And then if you have a Kelvin temperature, you would just take the Kelvin and subtract the 273.15, and that'll give you the Celsius temperature. So it's very easy to switch back and forth. We'll do a lot of switching back and forth with these temperatures later. Here's a little practice for you. Liquid nitrogen. I don't know if you've ever seen that in the Night of Science or in any other science show. It's very fun. But it boils at 77 Kelvin. Okay, what's that temperature in Celsius? So pause this, do that conversion. And so when we do that conversion, we would have to take the Kelvin, which is 77, subtract 273.15, and that'll give us the Celsius. Now, when I subtract this, I'm going to follow those sig fig rules. Remember, here I only have a tens and a ones place. We really didn't do a lot with sig figs yet, but we will soon. And so in my answer, I'm only going to keep my answer to the ones place. Like, I guess what I'm saying is I don't know the tenths and hundredths right here, for the original temperature. So I'm not going to keep tenths and hundredths in my answer. And so I'm going to round my answer off to the ones place, which is the smallest place I have here. And I get a negative 196 degrees Celsius. If you had negative 196.15, you did it right. It's just that you have to, basically later learn sig figs to be able to get this correct. So anyway, you should be able to define energy, the capacity to do work, classify its type as kinetic or potential, identify processes as gaining, which are endothermic, or losing, which are exothermic, and then, classify them as endo or exothermic. Law of conservation of energy, it's conserved during a change. Heat is total kinetic energy, temperature is average kinetic energy, and then know the conversions, among the Celsius, Fahrenheit, and Kelvin temperature scales to be able to practice those and put those into place. Good luck.